Okay, get ready, because today we're taking a deep dive into the world of advanced mathematics.
And while that might sound a bit intimidating, trust me, this stuff is seriously cool.
I am so ready for this.
We're talking about the kind of math that physicists use to understand the universe at its most fundamental level.
So we've got excerpts from this research paper, and it's dense, even for me.
But that's the beauty of this deep dive, right? We get to go behind the scenes of a paper normally only read by mathematicians and physicists.
Absolutely. And what we're going to uncover is how these VOSAs are being used to unlock some of the biggest mysteries in theoretical physics, particularly in string theory. Okay, so before we get too far, let's back up just a bit. For those of us who didn't spend our morning solving complex equations, what exactly is a VOSA?
Imagine you're trying to understand the symphony of the universe, the way all the particles and forces interact.
Well, string theory suggests that the fundamental units of this symphony aren't point-like particles, but tiny vibrating strings of energy. And that's where VOSAs come in. They provide the mathematical framework to describe the different ways these strings can vibrate and interact with each other. So instead of musical notes, we have these vibrating strings, and VOSAs are like the sheet music, telling us how they all come together.
That's a great way to put it. These EOSAs help us make sense of these complex interactions in a mathematically rigorous way.
Okay, so we're not talking about simple equations here. These VOSAs are more like the heavy-duty mathematical machinery that physicists use to model the universe.
Exactly. And just like any good piece of machinery, VOSAs come with their own set of rules and properties.
One of the key concepts is something called central charge. Think of it like a measure of complexity or a kind of energy budget for these mathematical structures. So, like how much energy a vibrating string can have.
Precisely. And the thing is, mathematicians are hard at work trying to classify different types of VOSAs based on their central charge and other properties.
So it's like they're trying to create a VOSA periodic table, organizing them by their unique characteristics.
Exactly. This research we're diving into today is a big step in understanding these properties, and as you'll see, it gets really interesting.
So let's get into the heart of this paper. It delves into two key properties of VOSAs: unitarity and strong graded locality.
Now, those terms might sound a little intimidating, but they're really quite intuitive.
Okay.
Think of it this way. Unitarity is like a law of physics, but for these mathematical structures.
Okay, so it's like a rule that has to be followed, a fundamental principle that governs how these VOSAs behave.
Precisely. It ensures that energy is conserved within these structures, which is a fundamental principle in the real world.
And strong graded locality. That's a mouthful, but what's it about?
It's about making sure that the different parts of a VOSA interact with each other smoothly. Think of it like a well-oiled machine where every part works together seamlessly.
So it's like a kind of compatibility check for the components of a VOSA.
Exactly. And these properties are crucial for mathematicians because they help us build elegant mathematical frameworks and connect those frameworks to other areas of mathematics and physics.
It's all about creating a consistent, coherent model of the universe.
Yeah, and that's where things get truly fascinating. This paper introduces some mind-blowing techniques for understanding the structure of VOSAs.
Okay.
They're called free fermion splitting and the neighborhood graph method.
Okay, those sound like something straight out of a sci-fi novel. Break them down for me.
Sure. Think about trying to solve a massive jigsaw puzzle. Free fermion splitting is like finding a way to break that puzzle into smaller, more manageable pieces. It helps mathematicians decompose complex VOSAs into simpler ones.
So it's like finding a way to break down a giant problem into smaller, more manageable pieces that are easier to work with.
Exactly.
And the neighborhood graph method. That one is a bit like drawing a map of all the pieces in the puzzle and how they relate to each other.
Yeah.
It creates a network or a graph that shows how different VOSAs are connected.
It's about visualizing the intricate web of relationships between these mathematical structures.
So we're not just solving the puzzle, we're also mapping out the connections between all the different pieces.
Precisely. And remember, the ultimate goal here is to classify all possible VOSAs. It's a monumental task, but every new discovery, every new technique gets us one step closer.
So it's like building that VOSA periodic table we talked about earlier. It's a never-ending quest, a quest to understand the fundamental structure of the universe.
Absolutely. And it's a quest that's fueled by human curiosity and ingenuity. It's a reminder that there's always more to learn, more to discover, and that the journey of exploration is often just as rewarding as the destination.
This is all so fascinating. We've talked about VOSAs, these intricate mathematical structures and these powerful techniques for understanding them. But what did the researchers actually discover? What were the big aha moments in this paper?
Well, one of the most significant findings is that they proved a whole bunch of VOSAs with a central charge of 24 or less actually fit the rules of unitarity.
Okay, let's unpack that a bit. We talked about central charge being like a measure of complexity for a VOSA. So are we saying that the less complex ones tend to be unitary?
Yeah, that's a great way to put it. The researchers focused on VOSAs with a central charge of 24 or less because those are often considered the building blocks for more complex ones. And what they found is that a vast majority of these VOSAs do indeed follow this fundamental rule of unitarity, meaning they conserve energy, just like physical systems in the real world.
So this is a big deal because it reinforces the idea that these abstract mathematical structures might actually have real-world connections.
Absolutely. It strengthens the link between this mathematical framework and the physical universe. Of course, it's still theoretical physics, but finding these connections is incredibly exciting.
Now, you know I love a good rule breaker. Are there any VOSAs out there that don't quite fit the mold, even with a lower central charge?
You're right. There are always exceptions that make things even more interesting. This paper specifically mentions the shorter moonshine VOSA and the odd moonshine VOSA.
Okay, those names alone deserve some kind of award. But what makes these moonshine VOSA so special?
Well, they're also unitary, but they have these unique properties that make them stand out from the crowd. It's like they have a different flavor or unique twist that sets them apart.
So even the rule breakers are giving us valuable insights. They're adding to our understanding of this whole VOSA landscape.
Precisely. And the way the researchers prove these results is incredibly elegant. They took what we already knew about certain types of unitary VOSAs and used some clever mathematical techniques to extend those results to a much broader class of VOSAs. It's like they solved one part of the puzzle and then used that knowledge to unlock a whole hidden section.
So where does this leave us? We've explored the world of VOSAs, these fascinating mathematical structures with their intriguing properties. What's the takeaway for someone who's just been introduced to this mind-boggling realm?
I think the biggest takeaway is the sheer power of mathematics. We're talking about concepts that are incredibly abstract, yet they have the potential to unlock some of the most fundamental mysteries of the universe. This research is a testament to human curiosity, our drive to understand the world around us, even at its most complex levels.
And while VOSAs and unitarity might sound like something out of a science fiction novel, they're a reminder that there's still so much we don't know. Who knows what amazing discoveries await us as we continue to explore the vast and intricate world of mathematics. And that's what makes this deep dive so rewarding. The journey of exploration is just as exciting as the destination itself.
Thanks for joining us as we ventured into the fascinating world of VOSAs. Until next time.
Ever feel like the universe is playing a game with rules we don't understand?
Yeah.
Well, today we're taking a deep dive into a research paper that's trying to crack those cosmic codes.
All right.
It's all about something called Vertex operator superalgebras. VOSAs for short. Sounds intense.
It can be.
Yeah.
Imagine trying to write the instruction manual for how particles interact on like the most fundamental level.
Wow.
That's the kind of challenge we're talking about.
Okay.
Yeah.
You've definitely got my attention.
Okay.
But particle physics, that sounds like some pretty heavy stuff.
Yeah.
What's the elevator pitch for why anyone should care about these VOSAs?
You'd be surprised. Understanding these structures could be a game changer.
Okay.
I'm talking quantum computers that make today's look like abacuses.
Wow.
And a clearer picture of what went down right after the Big Bang.
Okay, now you're speaking my language.
Yeah.
So we're not just talking about theoretical equations on a chalkboard.
Right.
There's real-world potential here.
Absolutely.
Okay.
The paper we're diving into is called Unitarity and Strong Graded Locality of Holomorphic Vertex Operator Superalgebras with Central Charge at most 24.
Okay.
It's tackling some big questions that have stumped physicists and mathematicians for decades.
I have to be honest, that title alone makes my head spin a little.
Yeah.
Let's break this down. Where do we even begin with something this complex?
A good place to start is with the VOSAs themselves.
Okay.
They're like the rule book for how particles interact.
Okay.
Imagine a cosmic dance floor.
Okay.
The particles are the dancers, and the VOSA lays out the steps and moves they can make.
So it's not just random chaos at the subatomic level.
Right.
There's a method to the madness.
Exactly. Now, this paper focuses on a particular type of VOSA called a holomorphic VOSA.
Mm-hmm.
Think of them like the most elegant and symmetrical dances on that cosmic dance floor.
Elegant and symmetrical. I'm picturing a perfectly choreographed waltz.
Okay.
But for particles.
You're on the right track. And in theoretical physics, symmetry is a big deal.
Mm-hmm.
It often points towards some deeper underlying principle at work.
Okay, I'm starting to get it.
Okay.
So we've got our cosmic dance floor.
Right.
And the holomorphic VOSAs are like the most elegant waltzes happening out there.
Right.
But this paper focuses on holomorphic VOSAs with a central charge of 24 or less.
Okay.
What's so special about that number?
That's a great question.
Yeah.
Central charge is essentially a way of measuring the complexity of a VOSA.
Okay.
You can think of it like the number of instruments in a symphony orchestra.
Okay.
A smaller orchestra might be able to produce beautiful, intricate music.
Mm-hmm. And a larger orchestra,
Yeah.
well, maybe more complex.
Yeah.
Might be more challenging to conduct,
Mm-hmm.
harder to keep all the parts in sync.
Exactly. The researchers here are focusing on these smaller orchestra VOSAs,
Okay.
the ones with a central charge of 24 or less,
Mm.
to really understand the core principles at play.
That makes sense. It's like trying to understand how a car engine works.
Right.
You wouldn't start by taking apart the most complicated engine ever built.
Right.
You'd start with something a little simpler.
Precisely. Now, with that foundation in place,
Okay.
we can start to dig into the really juicy stuff.
Okay.
Because this paper isn't just describing these VOSAs,
Mm-hmm.
it's trying to prove some long-held beliefs about them.
Okay.
Specifically, the ideas of unitarity and strong graded locality.
Okay. Those sound intriguing, but also kind of intimidating.
Yeah.
Let's start with unitarity.
Okay.
What's that all about?
In essence, unitarity is like a mathematical safeguard.
Okay.
It ensures that the predictions we make using VOSAs don't defy the laws of physics as we know them.
So it's like a cosmic rule checker, making sure our theories don't go completely off the rails.
Exactly. Okay, imagine trying to predict the trajectory of a rocket.
Mm-hmm.
If your calculations violate unitarity, that rocket might suddenly vanish or travel backwards in time. Not very helpful for space exploration.
Right.
Definitely
Yeah,
not.
right. And what about strong graded locality?
Okay.
That sounds even more mysterious.
This one's all about how information behaves at the subatomic level.
Okay.
Imagine you and I are playing a game of chess online.
Okay.
There are rules, right?
Right.
We can't just randomly move our pieces across the board instantaneously.
Right.
There are limitations built into the game.
So strong graded locality is like the rules of the game,
Yeah.
but for how particles interact across space and time.
You've got it. It ensures that information, even at the quantum level,
Okay.
can't just teleport around willy-nilly.
Right.
There are rules and limitations,
Mm-hmm.
and these rules are crucial for making sense of the universe at its most fundamental level.
Okay, I'm starting to get a sense of the scope and the challenge here.
Right.
We've got these incredibly complex mathematical structures, these holomorphic VOSAs,
Yeah.
and this paper is trying to prove that they adhere to these fundamental principles, unitarity and strong graded locality.
Exactly.
But how do they even begin to tackle something this complex?
Yeah.
What are the tools of the trade when you're dealing with cosmic code like this?
That's where things get really interesting.
Okay.
Because the techniques they use are almost as fascinating as the concepts themselves.
Okay.
One of the keys is a technique called free fermion splitting.
Free fermion splitting.
Yeah.
Okay, I'm definitely going to need you to elaborate on that one.
Okay.
Yeah.
Think of it like dismantling a complex machine to understand how each part works.
Okay.
That's essentially what free fermion splitting allows them to do with VOSAs.
Okay.
They break these structures down into smaller, more manageable pieces called free fermions,
Mm-hmm.
which we already understand pretty well.
So it's like taking our cosmic waltz and breaking it down into individual steps.
Right.
By analyzing each step, we can start to grasp the bigger picture of the entire dance.
Exactly. And what's even cooler is that through this process of free fermion splitting, the researchers uncovered a connection between holomorphic VOSAs and something called moonshine theory.
Moonshine theory.
Yeah.
Okay, now you're just messing with me, right? That sounds like something straight out of a science fiction novel.
I assure you, it's very real and very strange.
Okay.
It's this fascinating area of mathematics that seems to connect seemingly unrelated areas of math and physics in completely unexpected ways.
Wow.
It's like finding hidden passageways between different dimensions of mathematics.
Okay, you've definitely piqued my curiosity.
Okay.
How does moonshine theory tie into all of this?
Oh,
It sounds like we're about to enter some uncharted territory.
Buckle up,
Okay,
because we're about to go deeper into the rabbit hole and explore just that.
Okay, you've got me hooked.
Yeah.
I'm ready to dive into this moonshine theory and see how it all connects.
Okay.
But before we get too lost in the rabbit hole,
Right.
remind me again what this paper is actually trying to prove.
All right, we're talking about unitarity and strong graded locality.
Okay.
Remember, those are like cosmic rules, making sure that the math describing these VOSAs behaves in a way that aligns with the real universe.
Got it.
Yeah.
So how does moonshine theory fit into the bigger picture of proving these rules?
Well, it turns out that these holomorphic VOSAs, the elegant cosmic waltzes we were talking about,
Right.
share some interesting mathematical relationships with moonshine theory.
Okay.
It's like finding the same secret code embedded in two completely different places in the universe.
That's mind-blowing.
Yeah.
So these seemingly unrelated areas of math and physics are actually connected.
Exactly.
Wow.
And this connection provides valuable clues that could help us prove unitarity and strong graded locality.
Okay.
You see, the paper uses these insights from moonshine theory to build its proof.
Okay.
Almost like solving a complex, multi-layered puzzle. Each step builds on the previous one, gradually revealing deeper truths about these holomorphic VOSAs.
It sounds like a detective story unfolding in the realm of theoretical physics.
Yeah.
What's one of the key clues they use in this proof?
One of the most crucial elements is proving the complete unitarity of a certain structure within these VOSAs.
Okay.
It's a bit like proving that the foundation of a building is completely stable before you can even think about adding more floors.
I like it.
Yeah.
So they're making sure the foundation is solid before they build anything else on top of it.
Exactly.
How do they actually do that?
They leverage previous research on a special type of mathematical object called a lattice,
Okay.
which you can picture as a perfectly symmetrical grid of points.
Okay.
Now remember that lattice VOAs, arising from these lattices,
Yeah.
are already known to be completely unitary.
Right.
They essentially showed that the structure they were interested in could be embedded within a larger lattice-based framework, inheriting that crucial property of complete unitarity.
Wow. That's like borrowing the stability of a pre-existing structure to fortify their own proof.
Yeah.
That's clever.
It's a testament to the interconnected nature of mathematics often. By connecting seemingly disparate ideas, you can make significant progress in solving complex problems.
Right.
And this paper is a great example of that.
This is incredible.
Yeah.
I'm so glad we're exploring this together.
Yeah.
It feels like we're uncovering hidden treasures in the world of theoretical physics. But before we get ahead of ourselves,
Right.
what exactly does all of this mean for you and me?
Right.
How do these complex proofs and abstract concepts translate into real-world significance?
What's fascinating here is that while the math is undoubtedly complex, the potential applications of this research are incredibly concrete and relevant to our lives.
Okay, yeah, bring it on. I'm ready for the real-world stuff.
Remember how we talked about quantum computers being able to solve problems
Yeah.
that would take our current computers like billions of years?
Right.
Well, this research brings us closer to making those quantum computers a reality.
Okay, I'm seeing the connection.
Yeah.
Quantum computing is all about harnessing the strangeness of the quantum world.
Right.
Right.
Exactly.
But it's notoriously difficult to control.
Exactly. And that's where this research comes in.
Okay.
By proving the unitarity and strong graded locality of these special VOSAs, we're essentially establishing the ground rules for how information behaves in the quantum realm.
So it's like we're creating the safety regulations for building a quantum computer,
Yeah,
making sure it doesn't just short-circuit the universe.
that's a great way to put it.
Yeah,
Unitarity, that cosmic rule checker we talked about,
right,
is essential for ensuring that quantum computations remain consistent
right.
and don't lead to nonsensical results.
Okay.
And strong graded locality adds another layer of protection, ensuring that information within a quantum computer doesn't leak out
Right.
in a way that violates the laws of physics.
So it's like setting up the boundaries for these quantum computers to play within,
Well-
even if those boundaries are a little blurry by our everyday standards.
Precisely. And the implications go beyond just quantum computing.
Okay.
Remember our cosmic dance floor.
Yeah.
Well, by understanding the mathematics governing those elegant waltzing VOSAs,
Right.
we can actually peer back in time to the very early universe.
You're saying this could help us understand what happened right after the Big Bang?
Exactly.
Wow.
By understanding the rules governing particle interactions at that fundamental level,
Okay.
we can potentially create more accurate models of the early universe, shedding light on mysteries like dark matter and dark energy.
Wow. So we're not just talking about building better computers.
Right.
We're talking about unlocking the secrets of the universe's origins.
It's pretty amazing, right?
Yeah.
And like any good scientific breakthrough, this research doesn't just provide answers.
Right.
It opens up a whole new set of questions.
Like what?
Well, for example, this paper focuses on VOSAs with central charge 24 or less.
Right.
But what happens when we go beyond that limit?
Oh.
Are there even more bizarre and complex VOSAs out there, governed by completely different rules?
It's like we've just scratched the surface of a whole new universe of possibilities.
Right.
It makes you wonder what other cosmic codes are waiting to be cracked.
Exactly.
Yeah.
And another intriguing question is whether there are even deeper connections between VOSAs and moonshine theory.
Okay.
Could there be a more fundamental relationship there waiting to be uncovered?
It's both exciting and humbling to realize how much we still don't know.
Yeah.
But it's also inspiring to see how far we've come.
I agree.
Yeah.
It's a reminder that even the most seemingly abstract mathematical concepts can have profound implications for understanding the universe and our place in it.
This has been an incredible deep dive.
It has been fun.
We've explored some seriously complex concepts, but you've managed to make it clear, engaging,
Well, thank you.
and dare I say, even a little bit fun.
I appreciate that.
So for our listeners who might be feeling a bit overwhelmed, what's the one key takeaway you'd like them to remember?
Never underestimate the power of curiosity.
Okay.
Even if you don't fully grasp all the technical details, the important thing is to keep asking questions.
Yeah.
Keep exploring, and never lose your sense of wonder about the universe and its many mysteries.
Beautifully said. So for those of you ready to continue the adventure, we'll provide links to the research paper and some additional resources in our show notes. Until next time, keep exploring, keep learning, and keep diving deep.
Okay, so imagine, right, you're building this like huge Lego model, like the most complicated thing you can think of. And here's the catch. Some of the pieces, they like look like they should fit, but they just don't. Or like the connections are a bit off. So you're left wondering, is it me? Are these the wrong Legos?
Yeah.
Or am I missing something really basic?
I love that analogy. And honestly, that's kind of what it's been like for physicists. You know, working with these models, string theory, trying to explain everything at the smallest level. And the Legos, well, those are like these mathematical structures called Vertex operator superalgebras. VOSAs for short.
VOSAs, right. So this paper, Unitarity and Strong Graded Locality of Holomorphic Vertex operator superalgebras with central charge at most 24. That's like finding the missing instruction booklet then.
You got it. Huge deal in physics, huge G. Because it gives us a proof for certain types of these VOSAs, it proves they're unitary, which, trust me, is a really big deal.
Okay, so two things. One, back up just a tiny bit. VOSAs, what are they really? And like, why should people care, even if they aren't, theoretical physicists?
Right, of course. So think of a VOSA as a mathematical tool, a tool that helps describe symmetries, but at the quantum level.
Symmetries, okay, like a ball is symmetrical, you rotate it, it looks the same.
Similar idea, but we've gone subatomic. We're talking about the rules for how particles interact, how forces work, but in the quantum world, not our everyday scale.
So not about a ball, but more like the rules for how, I don't know, electrons interact.
Exactly. And those rules, man, they are key to understanding like the universe's source code.
Source code, love it.
Yeah.
But the paper title, it's got all this other jargon. Holomorphic central charge. What's that about?
Yeah, that's just getting specific. Which of VOSs are we talking about? You see, it's like all thumbs are fingers, but not all fingers are thumbs. So all holomorphic VOSs are VOSs, but not all VOSs are holomorphic.
Okay, so what makes a VOSA holomorphic? And why does it matter?
Basically, they're the well-behaved ones. They've got these really nice properties, mathematically speaking, that make them, well, let's just say they're really interesting, especially for string theory. And string theory, that's a whole other...
Oh, yeah, a theory of everything, right?
Yeah.
We could do another deep dive on that. But this central charge thing,
yeah,
what's the significance of it being at most 24?
Ah, good catch. So every VOSA, it has this number associated with it, the central charge. And it's related to, well, think of it like the dimensions of the theory. Now, this paper, they look at 24 because, well, string theory keeps pointing back to that number like it's some kind of key.
Okay, 24. Got it.
Yeah.
Magic number, maybe. But how does all this connect to unitarity? That word keeps popping up.
Excellent question. Because, see, in physics, our theory is they got to make sense, right? Can't just have things appearing out of nowhere. And unitarity, that's a principle that keeps things grounded in reality.
Reality. So, like, no particles just popping into existence.
Exactly. It's about probability, really. Things might be fuzzy at that level, but they can't just, like, vanish. Unitarity, it makes sure of that.
So it's like the universe's way of saying, nope, not going to happen. Got to follow the rule.
Exactly. And that is why this proof, this paper, it's a big deal. Because now we've got the math to back it up. These VOSAs, the ones that we think explain how things really work, they actually behave themselves.
No more hoping for the best, huh? We got proof. But how did they even figure that out? Proving it, I mean. Was it like just plugging in numbers?
Oh, I wish. No, this proof, it's clever stuff, seriously. They used all sorts of techniques, like one is called free fermion splitting.
Free fermion splitting. Okay, now that sounds complicated. Break it down for me.
Sure. So imagine you take this complex VOSA and you essentially break it apart into smaller, simpler pieces, like reverse engineering it. And by figuring out those smaller bits,
You can figure out the whole thing. Divide and conquer.
you got it. But they didn't stop there. They also used this thing called the neighborhood graph method.
Graphs. Like visuals. What do those have to do with VOSAs?
It's cool, actually. They're mapping out relationships between different VOS. Think of it like a map, right? Each point is a different VSA, and the lines show how they connect.
A VOSA social network. I like it.
And by doing that, by seeing those connections, they were able to use other things we already know, like certain types of VOSAs we knew they were unitary, so they built off of that.
So they took this super complex problem, broke it down, found hidden connections, and bam, proof. That's some detective work right there.
Right. Amazing stuff.
It really is. But what does it all mean? We'll unpack that and more right after this.
Yeah, this is big. It really is. And not just for the math people either. This proof, it changes how we see the universe. Or it could, at least.
Okay, so no more teasing. Hit me with the cosmic truth. String theory. It's correct now.
Yeah.
Solved. A black hole's going to show up in my backyard.
Whoa, hold on. We're not at the black hole stage just yet. But you're right to be excited, I mean it. This is big, like I said. Because before this proof, we just kind of assumed some things about these VOSAs, right? Like we figured they were probably unitary. It fit with what we saw in the universe.
So no more crossing our fingers, hoping for the best.
Exactly. This makes it way stronger. The idea that we're, on the right path. That string theory, these VOSAs, they're not just like math going crazy. They might actually describe the universe for real, at the most basic level.
Okay, that is huge. But aside from, like, proving what we thought we knew,
Yeah.
what does this unlock going forward? New research, new questions we can even ask now.
Oh, yeah. And that's the exciting part. It's like, imagine a dark room, right? We just flipped on the lights. So first, these techniques they used, right? The splitting, the graphs, that's not just for these visas. We can use that on others now, too.
So like a whole new set of Lego instructions
What?
for different models.
Exactly. But there's more. What about dark matter? We barely know anything about it. But some people, they think maybe certain VOSAs, they could describe those particles. And now we've got new tools to look.
So we might figure out dark matter because of a proof about some super abstract math. That's wild.
And we're not done yet. Quantum gravity, right. Our two best theories. Gravity and the quantum world. They don't mix.
Like oil and water. Or like that couple who should have broken up, but they just keep arguing at every party.
Haha, yeah, something like that. But finding a way to make them work together, well, everyone wants to solve that. And some people, they think VOSAs might be the key, the thing that connects it all.
This paper, it might have the answer to one of the biggest mysteries in physics. Wow, that's a lot.
It is more to learn for sure, more problems to solve. But it gives us a direction, we're not just lost anymore.
We've got a flashlight now pointing towards some very interesting places. That's why I love these deep dives. You start with something, honestly, it sounds kind of niche, right? Then, bam, biggest questions ever.
That's physics for you. Pushing those boundaries, the math, our imagination, and who knows where it goes. Maybe this proof is how we finally figure it all out.
Okay, so dark matter, quantum gravity.
Yeah.
Anything else got physicists buzzing about this? So we've talked about dark matter, we've touched on quantum gravity. Anything else got physicists buzzing about this?
Oh, absolutely. See, the paper, they really focus on VOSAs with that central charge of 24, right?
Right. The magic number. Like we said, maybe it's some kind of cosmic speed limit.
Kind of. But here's the thing. It makes you wonder, is 24 the only magic number? Or are there others?
Wait, hold up. Are we going full sci-fi now? Like other dimensions, universes next door?
Not quite, but think of it like this. The way they proved this, for these VOSAs, it all hinges on that number 24. What if, for other VOSAs, different numbers are important? Ones that maybe describe stuff we haven't even discovered yet.
So like instead of the periodic table with elements, it's like a table of important numbers for physics.
Exactly. And finding those numbers, who knows what it could unlock? New forces, new particles, whole new branches of physics even. It's exciting.
It really is. It's like we had a map all along, but instead of leading to gold or whatever, it leads to dot understanding. Like the universe's instruction manual, but way cooler.
I like that. And this paper, it's not the ending, it's the start. Now the real exploration begins, you know?
Totally. So anyone listening, next time you look up at the stars and go, whoa, big, just remember, we are just getting started. There's so much more to find out there.
Couldn't have said it better myself. Fun to be a physicist these days. Lots to figure out.
Absolutely. And on that note, we'll wrap up this deep dive. Huge thanks to our expert for, well, being an expert. And to everyone listening, stay curious, folks. We'll see you next time. Okay, so get this right. We're diving into some seriously mind-bending math today.
Uh-oh, should I be scared?
Well, imagine trying to understand, like, the basic building blocks of the universe.
Okay, I'm with you.
But instead of, like, atoms and quarks and all that, we're talking about mathematical structures.
Right.
Structures that might actually, like, govern theoretical physics. And that's where these things called vertex operator superalgebras come in. VOSAs for short, thankfully.
Catchy. And what's fascinating is we're not just talking about, any old math here. These are structures so fundamental they could help us understand reality itself. Or at least that's the hope.
Exactly. And you've been wanting to wrap your head around this new paper about these VOSAs, specifically these holomorphic ones.
Right.
And how they connect to something called graded local conformal nets, which sounds like a mouthful.
It's a bit of a mouthful, yeah.
And how this paper might be a big step towards proving that a lot of these VOSAs have this special property. Unitarity, they call it.
Yeah, that's the big one, unitarity. And that's exactly what we're going to try and unpack today. We'll break down the core concepts from this paper, talk about what VOSAs are, why they matter, why everyone's so interested in them.
Yes.
We'll explore this thing called the central charge.
Ooh, mysterious.
Especially the value 24, which keeps popping up. And we'll see how it all ties into the construction of those graded local conformal nets you mentioned.
Okay, so let's unpack this. Can you give us a simple way to think about VOSAs? Because I'll admit, when I first saw them, it was like my brain did a backflip.
Yeah, they're not exactly intuitive, are they? Think of VOSAs as like, intricate rule-based systems. But these rules, they help us describe, or at least try to describe, certain aspects of theoretical physics. They pop up in a field called conformal field theory, if you've ever heard of that.
You have, yeah.
Which deals with symmetries, how things behave when you stretch or squash space-time.
Whoa.
In specific ways, at least.
Okay, so we're talking about the very fabric of reality, but on this mathematical level. It's kind of blowing my mind. But why should we even care about VOSs? What's the big deal with these things?
Well, they're not just theoretical curiosities, even though they sound like it. VOSAs have some potentially big applications.
Oh, yeah. Like what?
Like, they can help physicists study things like string theory, which you've probably heard of, which is attempting to unify, all the fundamental forces in the universe. And they help mathematicians explore higher dimensions. So they're pretty powerful tools.
So VOSAs are like the secret decoder ring for some of the universe's biggest mysteries. I like it. Now, this paper, it keeps mentioning central charge and this number 24. What is so special about 24? Is it like the cosmic number of the day or something?
You're definitely on to something. The central charge, it's a numerical value tied to a VOSA. It's like, it's a bit like a fingerprint. And it turns out a central charge of 24, that's a really interesting one. It pops up in string theory and certain mathematical symmetries. Mathematicians, they've been studying VOSAs with a central charge of 24 like crazy because they seem to have these unique properties.
Interesting.
Think of 24 as like a mathematical sweet spot where things get really interesting.
This is where it gets really interesting, I feel. It's like we're on this quest, right, to find these special VOSAs with the right properties to make them make sense in the real world. And the paper calls these special ones unitary VOSAs. Right.
Exactly. Unitarity is all about, well, it's about ensuring that the models we build, they don't lead to crazy nonsensical predictions about the universe, like time flowing backwards or something.
Yeah.
Not very unitary.
Okay. So unitarity keeps our mathematical universes grounded in some kind of reality. So how does this paper actually help us find unitarity?
It actually proves the unitarity of many, though not all, holomorphic VOSAs with central charge 24, and even some with smaller central charges, which is pretty cool.
How do they do that?
Using some seriously clever techniques, like they use something called free fermion splitting, which is basically like breaking down a VOSA into smaller, more manageable pieces, like a puzzle.
Yeah.
They also use the neighborhood graph method to analyze the relationships between different VOSAs. And they even use these things called dual pairs and simple current extensions to build more complex VOSAs from simpler ones.
So they're like reverse engineering these things, breaking them apart, putting them back together, just to figure out how they work.
Essentially, yes. It's like taking apart a car to see how the engine works, but with math.
Okay, I can dig it.
And by proving unitarity for these VOSAs, the paper is saying, hey, these mathematical structures, they might actually describe something real out there.
Mind blown. This is why I love math. It's like peeking behind the curtain of reality.
It is exciting stuff. And what makes it even more exciting is how this all connects to those graded local conformal nets we talked about. Remember those?
Right. Those were another thing that had me scratching my head.
Yeah, they're pretty out there.
Can you, remind me what those are about?
Okay, so think of conformal nets as another layer of mathematical structure on top of everything else we've been talking about. But these represent the actual physical observables in a quantum theory. So imagine you're trying to measure, like, the spin of an electron.
Okay.
The conformal net, it gives you a way to describe that measurement mathematically. It's how we formalize that.
So it's like going from a blueprint to actually building the house. That's a good analogy.
Yes, exactly. And this paper uses the unitarity they've proven about these VOSAs to build those nets. It makes sure that they're well-behaved, that they don't completely contradict what we know about physics. It's like a quality control check for mathematical universes.
I like it. So we've got our VOSAs, we've got unitarity, we've got conformal nets, all these pieces fitting together. What are the tools they use to actually build these nets, though?
Well, they use concepts like strong graded locality to make sure everything is consistent, and energy boundedness, so nothing explodes in our theoretical models, which is generally a bad thing.
Right. Exploding universes, not good. It's all starting to make sense. But I bet there are still some unanswered questions.
Right.
That's how science works.
Of course. Yeah, even with these breakthroughs, there are still VOSAs out there whose unitarity is still a mystery.
Really?
Especially those with a central charge of 24 and a few other quirks the paper gets into.
It makes you wonder if they could use, the methods in this paper to solve for those too, right? Imagine what they could find.
Right.
It's like we're on the edge of some new mathematical frontier, and this paper is the map. But how did they even go about proving unitarity in the first place? Did they, lock themselves in a room with a whiteboard for a year?
There was probably a whiteboard involved, yeah. But the paper actually, it walks us through it. For VOSAs with central charge 24, they start by looking at what are called their even parts, which are regular VOAs, not even super ones.
Okay, so they simplify things a bit before jumping into the super world.
Exactly. They focus on something called the dual pair associated with the VOSA's even part. So we've got these two VOAs, W and VK, that kind of live inside it.
Right, W being the Heisenberg coset and VK being the lattice VOA.
You got it. And they prove that the tensor product of these two, WEA, VK, that it's completely unitary.
And complete unitarity means?
It means that not only is the VOA itself unitary, but all its modules, kind of like its building blocks, those are all unitarizable as well.
Okay, so it's like super duper unitarity. How do you even go about proving that?
It's kind of a chain of reasoning. They build on previous work, other papers. So first, they use this result that says, essentially, that if a strongly rational VOA has a pointed modular tensor category, meaning its modules are all simple currents and it's strongly unitary, then it's automatically completely unitary.
So they just had to show that WEVK meets those criteria and bam, complete unitarity.
Well, not quite. They still have to show that WEVK is strongly unitary.
Right, just because something could be unitary doesn't mean it actually is.
Exactly. And to do that, they use a few tricks. They use another result from another paper that says twisted modules of lattice VOAs, those are unitary under certain conditions.
Lattice VOAs being those that come from, lattices.
Right. And they apply that to VK. Then they use this cool result that says fixed point subalgebras of holomorphic VOAs. Those are also completely unitary under certain conditions.
Fixed point subalgebras. Those are the ones that stay the same after a specific transformation ramp.
You got it. And they use that for W, since you can write it as a fixed point subalgebra of a lattice VOA.
So they're using what we know about lattices, fixed points, and these clever connections to get to the complete unitarity of WVK.
Exactly. Perfectly said. And once they have that, they use some general results about VOSA extensions to prove that V0, the even part of our original VOSA, is also completely unitary.
V0 being a simple current extension of WUVK, if I remember correctly.
You're on fire today. And since they know that V0 is completely unitary, they can conclude that our original VOSA, V, that's also unitary.
So they build it up from the ground up.
Yeah.
Using these dual pairs and connections, proving unitarity step by step. Amazing. But what about the VOSAs with the smaller central charge? They didn't just forget about those, did they?
Definitely not. This is where that free fermion splitting comes in handy, remember that?
Right.
They basically show that for any nice holomorphic VOSA with a smaller central charge, you can essentially tack on these free fermion VOSAs until you bump up the central charge to 24.
So you just keep adding ingredients until you hit the magic number.
Yes, like a mathematical recipe. And since the free fermion VOSAs are already known to be unitary, and they've proven it for those with central charge 24, they can conclude that those smaller ones also unitary.
So elegant. It's like they've built a unitarity machine. You put in a VOSA, crank the handle, and out pops unitarity.
You're making it sound way too easy. But you're not wrong. It's a cool result.
You mentioned that there are some VOSAs where unitarity is still a mystery, even with that magic number of 24. What's the deal with those?
Yeah, the paper talks about these VOSAs with central charge 24. They have these non-trivial odd parts, meaning they're true superalgebras, not just VOAs in disguise, but they have this vanishing weight 12 subspace. And that makes things tricky.
Weight 12 subspace. Now you're just making up words.
I know. Remember how VOSAs have these conformal weights associated with their elements?
Yeah, like energy levels, right?
Exactly. Well, the weight 12 subspace is just all the elements that have a conformal weight of, you guessed it, 12. And these mystery VOSAs, they don't have any, at least not in that weight class.
So they're missing a piece of the puzzle.
Exactly. And without that piece, a lot of the normal techniques they use to prove unitarity, those don't work.
So that's the next challenge,
Yeah.
figuring out how to handle those VOSAs that don't play by the rules.
You got it. It's a problem that will keep mathematicians busy for a while, I'm sure.
Now, what about that strong graded locality? We were talking about that earlier. We've been so into unitarity. I feel like we've neglected its cousin.
Oh, you're right. Good point. Let's loop back to that. So strong graded locality is what lets us go from a unitary VOSA to a graded local conformal net, which is the goal here, ultimately.
Right. Those nets help us describe those physical observables, like we were saying.
Yes, exactly. And this paper, it doesn't prove strong graded locality for all the VOSAs, but they get pretty close. They focus on the ones with central charge 24 and these non-trivial odd parts.
So the really super ones.
Right, exactly. And to prove this strong graded locality thing, they need to show a few things. First, they got to show that the VOSA is energy bounded. So like the energy levels of its elements don't go completely haywire. They also have to demonstrate this strong intertwining property and the strong braiding property for its intertwining operators.
Intertwining operators. Those are the things that let us combine different modules, right?
You got it. They're like the glue holding the VOS's building blocks together. Now, to prove all of this, they go back to those dual pairs we were talking about. They look at these specific VOAs, E and X.
How do they even choose which ones to use?
It depends on the VOSA's gluing type, which is basically just how its simple currents are put together.
Simple currents being those modules you can use to extend the VOSA, right?
Right on a roll. So if the VOSA is what they call gluing type I or I, they use W, that Heisenberg calls it, for E, and VK, the lattice VOA, for X.
The same ones from the unitarity proof.
Exactly. But if it's gluing type 3, things get a bit more complicated. They have to look at the VOSA's stump. That's what's left after you remove all the free fermion parts.
Stripping it down.
Exactly. And they set E to be the even part of that stump, and X to be the Virasoro VOA with central charge 12.
Virasoro VOAs, those are the ones describing those symmetries in string theory, right?
See, you remember all the important stuff. Now, it doesn't matter which E and X they pick. They prove that both E and that tensor product, EEX, they have some pretty nice properties.
Like what? Give me the good stuff.
Okay, so they're completely unitary, strongly local, meaning their operators are well-behaved, completely energy-bounded, and their intertwining operators, they have that strong intertwining and braiding.
They've got everything they need.
Right. And this is where it gets really cool. This lets them use this really powerful result about something called the strong integrability functor.
Okay, now you've lost me.
Basically, it's a way to connect VOSAs to conformal nets.
Okay, so it's like a mathematical wormhole?
I like that. So using this functor, they showed that this tensor product net, AX, that's completely rational, meaning it has a really well-behaved representation theory, which is what mathematicians love. And this lets them build a graded local conformal net extension, AVEEX, which is a mouthful, but the important thing is it's got a non-trivial Fermi part, so it's a true superalgebra, and its Bose part is just the conformal net from the even part of our original VOSA.
Okay, so they built the conformal net, and it all goes back to those dual pairs and the properties of E and X.
Exactly. They even show that this net extension is holomorphic. It's got only one irreducible representation, and it's the only one with those properties, which is huge.
So they found the one true net.
Well, kind of. It's the net that perfectly describes our VOSA. But you're right, it's a big deal.
They linked the VOSA to the conformal net, proved its strong graded locality. That's amazing. But you said they didn't do this for every VOSA.
Right. The tricky ones are the ones with gluing pipe 3, central charge of 24, and a trivial weight 12 subspace.
Those ones just refuse to follow the rules.
It's like they're the rebellious teenagers of the VOSA world. Their structure is just more complex.
Speaking of those rebellious VOSAs, you mentioned earlier those non-typical ones. The gluing type 3 with the trivial weight 1 subspace. What makes those so weird?
They just don't fit in with the others. There are two in particular. There's VBO, which is, get this, a fusion of the shorter moonshine VOS with a real free fermion VOSA. And then there's VO, the odd moonshine VOSA.
Moonshine VOSAs. Sounds like something out of a science fiction movie.
Oh!
But are these moonshine ones unitary too?
They are. VOF, that one's pretty straightforward. The shorter moonshine VOSA and the real free fermion VOSA are each unitary on their own, so if you combine them, it stays unitary.
So it's like mixing two stable chemicals together, you get something that's still stable.
Exactly. But VO, the odd moonshine one, that's a bit trickier. The paper talks about how its even part is basically a fixed point subalgebra of the Leech lattice VOA.
Reach lattice. That rings a bell. Why do I know that? Yeah. Wasn't that important for sphere packing or something? Something about it being really efficient.
That's the one. Mathematicians love that thing. So we know that the Leech lattice VOA is unitary, and other people have shown that under the right conditions, fixed point subalgebras of unitary things are also unitary. So they conclude that VOA, it's unitary too.
So even the weird ones seem to have unitarity. It's like it's just built into these holomorphic VOSAs, at least up to a central charge of 24.
That's a really interesting observation. And, a lot of mathematicians think that might be true, but actually proving it, that's a whole other challenge.
Another mystery for the math world to solve. Okay, before we go too far down that rabbit hole, let's bring it back for everyone listening. We've thrown a lot of terms around. VOSAs, unitarity, conformal nets, moonshine, the whole shebang. What's the big takeaway from all of this?
I think the biggest thing is this research. It's like trying to read the universe's source code. These structures, they might be the fundamental things that make reality work the way it does. And even though the math is, it's pretty out there, the implications could be huge.
So what could this actually lead to concretely?
Well, imagine breakthroughs in quantum field theory, like a much deeper understanding of particles, forces, all of that.
Okay.
Or big leaps forward in string theory, maybe even a unified theory of everything. Who knows?
That would be incredible.
And, on a more practical level, these tools, these mathematical tools we've been talking about, they could revolutionize other fields. Computer science, engineering. The possibilities are pretty mind-blowing when you think about it.
So even though I don't fully understand all the details, it's clear that this is really important stuff. This could change the world.
Exactly. And that's what makes this field so exciting. Who knows what we'll discover next?
So that was quite a journey. You've given me a whole new appreciation for abstract math. I never thought I'd say that.
It's been my pleasure. Math can be pretty awesome, even if it's a bit strange sometimes.
That's for sure. And to everyone listening, thanks for joining us on this deep dive into the world of VOSAs. We hope you enjoyed it as much as we did. Until next time, keep those minds curious.
All right, today's deep dive takes us into a world of math that's got a surprising link to the universe. We're talking about vertex operator superalgebras, or VOSAs for short.
VOSAs are like a mathematical language that describes the fundamental building blocks of reality.
Think of it as trying to understand the universe not through telescopes, but through equations.
Exactly. They provide a purely algebraic way to express how quantum fields behave. Those fields are the tiny fundamental pieces that make up everything around us.
So we're using algebra to describe the rules governing these quantum fields. That's pretty mind-blowing. What are these vertex operators you mentioned?
Imagine a giant cosmic play. The vertex operators are the action verbs in that play, telling the quantum fields what to do. They describe how the fields interact, exchange energy, and pass information.
So the vertex operators are like the action verbs of this quantum play that makes it easier to visualize.
It does, right? But here's where it gets really interesting. The study we're looking at focuses on VOSAs with a central charge at or below 24. This central charge acts as a kind of numerical fingerprint that tells us a lot about the VOSA's properties.
Like a unique identifier for each VOSA.
Precisely. Now, the study uses a bunch of big math terms like conformal field theory, or CFT, and graded local conformal nets. What's the connection between those and VOSAs?
You're right, these are big words. How do these things connect to understanding the behavior of quantum fields?
Here's the thing. VOSAs and conformal nets are like two sides of the same coin. Imagine you have a complex system, like a network of interconnected roads. VOSAs provide the equations that govern the flow of traffic on those roads.
Okay, so they tell us how the traffic moves.
Exactly. But what about the map of the roads themselves? How are they connected? That's where conformal nets come in. They provide a way to visualize and analyze the network structure of these quantum fields. Think of them as maps of the quantum world.
So VOSAs are like the traffic laws and conformal nets are like the maps.
You got it. And this study made a fascinating discovery about these VOSAs.
It's got to be something big.
It is. The study shows that almost all nice holomorphic VOSAs with a central charge of 24 or less and a non-trivial odd part are unitary.
Nice. Holomorphic, what does that mean? And what in the world is unitary?
Don't worry, nice is just a math term for VOSAs that have certain desirable properties, making them easier to work with. As for holomorphic, it refers to a specific type of function, like a mathematical blueprint that describes these VOSAs. And unitary has to do with quantum systems preserving probabilities.
Okay, so these nice VOSAs are well-behaved, and unitary means that they obey the rules of quantum mechanics.
Exactly. This is a big deal because it means these VOSAs can be described using something called Hilbert spaces.
Hilbert spaces. Is that something I should be worried about?
Not at all. Hilbert spaces are basically the mathematical playgrounds where quantum mechanics unfolds.
So, by proving that these VOSAs are unitary, the study shows us that they fit neatly within the framework of quantum mechanics.
Exactly. And that gives us a deeper understanding of how certain quantum field theories might work at a fundamental level.
So we're using these mathematical tools to unravel the mysteries of how the universe works.
You got it. And it gets even more intriguing. The study also dives into this short moonshine conjecture, which is an unsolved problem in math.
A mystery! This is getting exciting. Tell me more.
This conjecture revolves around the uniqueness of a specific VOSA. Imagine a giant puzzle, and there's one elusive piece that seems to hold the key to solving the whole puzzle. That's what the short moonshine conjecture is like.
Wow, it's like the missing link in our understanding of how certain quantum field theories work.
Precisely. And to tackle this puzzle, the study uses a special type of VOSA called lattice VOAs.
Lattice VOAs, what makes them so special?
Lattice VOAs are built from mathematical structures called lattices. Imagine a grid or a honeycomb. Those repeating patterns are mathematical lattices. Lattice VOAs capture the essence of these repeating patterns within the realm of quantum fields.
So they're using the geometry of these lattices to understand the quantum world.
That's a great way to put it. They act as fundamental building blocks. By studying these lattice VOAs, we gain valuable insights into the properties of other, more complex VOSAs. It's like figuring out the alphabet of a language. Once you understand the basic letters, you can start to decipher words and sentences.
Okay, so lattice VOAs are like the ABCs of this quantum world.
That's a good analogy. And now we've got one more key concept to discuss. Strong graded locality.
Strong graded locality. Sounds pretty technical.
It is. Remember how we talked about conformal nets acting like maps? Strong graded locality is like a set of rules that govern how these maps are structured. It's about the arrangement and order of interactions within these quantum networks.
So it's not just about the connections between the quantum fields, but also the order in which they interact.
Exactly. And the study found that many of these VOSAs are strongly graded local, which tells us a lot about how their corresponding conformal nets behave.
So there's a specific order that these quantum fields interact, and that actually matters. It's like we were saying, it's like realizing there's a specific traffic pattern on those quantum maps we talked about.
Precisely. And just like understanding those traffic patterns helps us optimize the traffic flow, understanding the strong graded locality helps us understand how information flows within these quantum networks. This is really crucial for building a more complete picture of how these quantum fields influence each other.
Okay. I'm starting to see the significance of this whole strong graded locality thing. But what does this finding about these VOSAs actually mean in the grand scheme of things?
Well, this is where it gets really, really fascinating. Proving that many VOSAs are strongly graded local leads to the creation of what we call holomorphic graded local conformal nets. And these nets are, well, they're incredibly useful tools in theoretical physics.
Hold on a second. Holomorphic graded local conformal nets. Can we maybe break that down a little bit? For those of us who don't, speak fluent physicists, what are we really talking about here?
Of course. So think of holomorphic in this context as a badge of honor for these conformal nets.
Sure.
It means that they have these special properties that make them particularly well behaved mathematically. And then graded local, like we discussed, that refers to that rule-based structure that we were talking about, the order of interactions within the net.
So they're like the VIPs of conformal nets. They've got the special access pass to the inner workings of the universe.
That's a fantastic way to put it. They provide physicists with incredibly detailed blueprints to understand how these quantum fields operate and how they interact with each other.
It's like having a more precise map with much clearer directions, only this map is one that helps us navigate the complex world of quantum physics.
Exactly. Now you might be wondering, what does this all mean in the bigger picture?
Yeah, we've gone pretty deep into the weeds of math here. How does this study actually change our understanding of the universe?
Okay, so this study significantly advances our understanding of VOSAs and their close connection to conformal field theories. And it highlights just how crucial unitarity and strong graded locality are for really unraveling the secrets of the universe's fundamental building blocks.
So this research is really pushing the boundaries of what we know about how the universe operates at the most fundamental level.
Exactly. It's like we've been handed this new key to unlock these deeper layers of understanding about the universe. And that brings us to one of the most exciting parts of this research. It poses this really intriguing question. Are all nice holomorphic VOSAs with that central charge of 24 or less strongly graded local?
It sounds like we've stumbled upon another one of those universe-sized mysteries.
We have. This question has the potential to open up this whole new avenue of exploration. Imagine a universe of mathematical structures all potentially explained using these incredible tools, VOSAs and conformal nets.
It's like we're standing at the edge of this vast, uncharted territory with a map in hand and a thirst for discovery. This deep dive has been quite the journey. We've explored the world of Vertex operator superalgebras, discovered their connections to conformal field theories, and even glimpsed those tantalizing mysteries surrounding the short moonshine conjecture.
And don't forget about those intriguing non-typical VOSAs.
Oh, right. You mentioned those a bit earlier. What's their story?
Well, there are two that are particularly interesting. First, we've got the graded tensor product of the shorter moonshine VOSA, denoted as VB, with a real free fermion VOSA, denoted as VBA.
Okay, that's a mouthful. Then the second one?
The second one is called the odd moonshine VOSA, denoted as VOA. Both of these kind of fall into that category of VOSAs with a central charge of 24, but they have these unique quirks that make them stand out.
So they're like the rebels of the VOSA world. They're marching to the beat of their own drum.
You could say that. They don't quite fit into the neat categories of those three gluing types that we talked about earlier. Their structures and properties are still being actively explored, adding another layer of complexity and intrigue to the world of VOSAs.
So does this new research, with its focus on unitarity and strong graded locality, does it shed any light on these non-typical VOSAs?
It does. The study actually confirms the unitarity of both VOF and VOS, making them even more significant to our understanding of VOS. This means they can be described within the framework of Hilbert spaces, just like those other nice VOSAs we've been talking about.
Even the rebels have to follow the rules of quantum mechanics. That's pretty cool. It seems like these non-typical VOSAs might hold some crucial pieces of the puzzle, even if they don't fit neatly into the existing classifications. It just goes to show that the universe of mathematics, much like the actual universe, is full of surprises. So before we wrap things up, I have to ask about this shorter moonshine VOSA that we keep coming back to. It almost sounds like something out of like a fantasy novel or something.
It is a bit of a mathematical enigma, this shorter moonshine VOSA, denoted as VB. It's a special type of VOSA with a central charge of 472, and its uniqueness is still a subject of intense research.
So it's like this VOSA is holding on to its secrets and daring mathematicians to try and crack the code.
Exactly. The shorter moonshine conjecture, like we've touched upon, proposes that this VB is the only nice holomorphic VOSA with those specific properties. Proving or disproving this conjecture would have some pretty significant ramifications for our understanding of VOSAs and their connection to these broader mathematical and physical theories.
It sounds like a challenge worthy of the greatest mathematical minds. And before we wrap up, I also wanted to circle back to those non-typical VSs. You mentioned those earlier, the ones that are related to this shorter moonshine VOSA. What's their story?
Ah, yes. There are two that are particularly fascinating. First, we've got the graded tensor product of the shorter moonshine VOSA, VB, with a real free fermion VOSA, which is denoted as VOs. And then there's the odd moonshine VOSA, which is denoted as VO. They both kind of fall into that category of VOSAs with a central charge of 24, but they have these unique characteristics that make them stand out.
So they're like the rebels of the VOSA world, kind of breaking the mold.
In a way, yes. They don't quite fit the neat categorization of those three gluing types that we talked about earlier. Their structures and properties are still being actively explored, which adds another layer of complexity and intrigue to this whole VOSA universe.
And this study, with its focus on unitarity and strong graded locality, does it shed any light on these non-typical VOSAs?
Absolutely. The study actually confirms the unitarity of both VOF and VOA, further cementing their importance in our understanding of VOSAs. This unitarity implies that they too can be described within the framework of Hilbert spaces, just like those other nice VOS we've been talking about.
So even the rebels have to follow the rules of quantum mechanics.
It seems so. This finding strengthens the case for these non-typical VOSAs being these essential pieces of the puzzle, even if they don't fit, neatly into our existing classifications.
It's a good reminder that the universe of mathematics, much like the actual universe, is full of surprises and wonders that constantly challenge our assumptions and really expand our understanding.
Well said. The journey of exploration is far from over, and this deep dive has only just scratched the surface of this fascinating field. The more we learn about VOSAs, the more we realize how much more there is out there to discover.
It's a testament to the power of human curiosity and this endless pursuit of knowledge. We've delved into this intricate world of Vertex operator superalgebras. We've explored their connections to conformal field theories, and we even glimpsed those really tantalizing mysteries that surround the shorter moonshine conjecture and these non-typical VOSAs.
We've really seen how these mathematical structures, these VOSAs and conformal nets, are helping us to map out and understand these fundamental forces that shape the universe. It's a journey that's both intellectually stimulating and honestly deeply inspiring.
And as we've learned, the journey is far, far from over. There are countless mysteries that are still waiting to be uncovered, countless questions still waiting to be asked.
So to our listeners, we encourage you to keep exploring, keep questioning, and keep diving deep into the wonders of the universe, both mathematical and physical. There's always something new to learn, something new to discover.
And who knows, maybe one of you listening will be the one to unlock the secrets of the shorter moonshine VOSA, or maybe even chart those unexplored territories of the VOSA universe. Until next time, keep those minds curious and keep those imaginations ignited.